start recording, start stream. And then as always, I got to hop into X and make sure that it is working. And then I'm going to invite everybody. And I would encourage everybody here, if you are on X and you are following Tashi and you see the live stream going on, to tell everybody about it. Get them to watch the stream. I'm also happy to have people join us in Discord. This is where people are going to ask questions, right? So let me go ahead and post this real quick. Join me on today's community update. All right, let's see if we can get some folks to join us there. Perfect. All right, we are off to the races. I'm having an issue with the chat. Let me see, figure out what's going on with the chat stuff here. Embedded chat. All right, so it seems to be that I'm having an issue with the OBS plugin for chat. There we go. Okay, we're good. We are live. We're ready for today's community update. And I just have to make sure I am sharing in two places because I want to make sure everybody in Discord gets the tier 1 treatment because y'all are here with me and that's important. So there we go. Thank you for reposting the stream. Crypto Hunter, you are a gentleman and a scholar. And actually, I'm going to have a surprise for you coming up here pretty soon. Nobody else knows about it yet, so we're going to keep it on the hush for a little bit. But your name came up yesterday in a discussion with the internal team. So, we'll announce it soon, but it is going to be showing our gratitude for your much support and specifically for your video and helping out the community. We want to be able to recognize folks in our community, specifically in Discord. We're a small, scrappy team. We're just trying to solve problems and build technology. And so we don't always have time to answer everything in Discord. And so those of you that are in Discord and helping out with helping people navigate the technology and understand how to kind of problem solve their own issues when it comes to Lattice or Vertex, we try to get in there if there's something new that we can help with. We want to get in there. And if there's a ticket raised, we have a support team that handles all of the tier 1 support issues. But we also want to make sure that, on the day-to-day, there are just operational things we got to do to maintain our nodes or to participate in the ecosystem. And those of you that are participating, we can't thank you enough. You guys are awesome. All right, so we got a group who is joining us now. A few people here in Discord. By the way, if you're watching this on X, Discord, if you join in Discord, you can ask a bunch of questions there. And that's kind of where our community is. If you're wondering where our Discord is, just follow the link tree on the X Tashi profile, so Tashi protocol profile, and you can get into our Discord and then join the stage every Tuesday. Now, I will make a little housekeeping announcement today. I am not going to be here next week. I'm going to finally take a vacation after... what's it been? Almost 9 years in the crypto space. I have not taken a real vacation. I have been on holiday with family and I have taken my computer and I have worked in the mornings and the evenings, even while I was on vacation. Next week is probably going to be my first vacation where I am not bringing my computer and I am uninstalling all of my business apps. So I will... only those who know me closely will be able to reach me through my phone number. And Amar, our CEO, will definitely have access. So if any emergency comes up in the Tashi space, he has access to me. But I'm going to be pretty much unreachable next week. My daughter and I are going on a trip. So it'll be my first time in 9 years taking a break. So next week, we are not doing the community update, but we will be doing it the following week. So today's topic, this is exciting to me, and I hope it's as exciting to you as it is to me, because I think today's topic is really talking about the Tashi consensus pattern and why it's so different. A few weeks ago, we talked about specifically why lattice and vertex were important and how arc and lattice and vertex all play together. But I want to talk specifically because we're refactoring the vertex code. And we're just about done with that. And I'm really excited about that because all of this really comes down to who can use this consensus at the edge, right? So if we think about what we're building, we've built a consensus protocol. And actually, you know what? Why don't we just hop in? I've got a shared whiteboard. Why don't I just share? I'm going to go to the shared whiteboard. Let me do a share screen here. Boom. All right, can you guys see that shared whiteboard? I'm going to move it over here so that I can. Okay, cool. I think everybody can see this now. All right, so kind of to give you an idea of what we're building, a few weeks ago we talked about, let's see, where is it? Scroll back to content. Is the page working? Oh. Well, that's unfortunate. My browser froze. Let's see here. Oh, interesting. Okay, one sec. That app, for whatever reason, decided to crap out on me. Let's go back to our app. Ah, there we go. Boom. All right, everybody can see that. Okay, so last time we talked about it, I drew out this little thing here and talked about Vertex and Lattice and Arc, and the goal of Vertex was to create kind of this peer-to-peer consensus. And so each one of these little diamonds here represents Vertex. Can you see it now, Crypto Hunter? It kind of, oh, actually you can't. Let me try this again. Oops, that's not the one I want to share. Let's share a different one. There we go. Can you see that? Boom, there we go. Okay, much better. So last time we spoke, we talked about Vertex. Each one of these little diamonds represents a Vertex instance, meaning that you've got a device, a computer or a robot that is running Vertex, and it is synchronizing with other members in a Vertex session. This is distinctly different from how most of blockchain operates. So let me talk real quick about the refactor, and then we're going to kind of compare and contrast the two, okay? So in this case, we said we have robots. I think, I don't know what each of these players, MB, I don't remember what MB was, but we got different things here. So if we take one of these robot diamonds here, right, and we blow it up, really what we've got inside of this is we've got a little Vertex core library that lives inside of this wrapper. Okay, so we got Vertex core library. And this is going to be a little technical today, but I hope that it's useful to everybody so you kind of understand what we're building. So this is built in Rust. And there's a few things going on here, but we'll just say that this library, we'll call this our RoboMesh library, right? This is me kind of, there we go, on the fly naming this, but we'll call this our RoboMesh SDK, right? This is really maybe something for like ROS2. It's a ROS2 plugin, right? And this is going to be written in likely Python or C++. There we go. Right, so we have this RoboMesh SDK. Now the difference is like, so Vertex itself is a library that has all of the features that you need to establish consensus between peer devices. But that's not really useful on its own. Well, if you're savvy and you know how to use it, it's useful on its own. But if you don't know how to use Rust or C++ and just the wrapper on the outside, maybe you're in the robot space building robot software, you understand ROS2 really well, right? And ROS2 comes in a couple flavors. I believe it's C++ and Python. But you understand ROS2. You understand how to use the language and the SDK and the framework of ROS2 and with their plugin ecosystem to get robots to do what you want them to do. And that's your expertise. Understanding Rust, a separate language, and maybe even understanding the Vertex library is not what we expect you to understand. And that's kind of where we are right now, where we've got this Vertex library that anybody can plug in and use in their application. The problem is like, you're not an expert in these things. And let's be real, if you're building robot solutions, you're not really interested in going out and learning a new language or a new library or anything like that. You are familiar with ROS2. So there needs to be a connector that lives between the two. So if we move that to, say, up here, there has to be like some type of connector that lives here, right? That basically connects the ROS2 interface to the Rust Vertex interface. Okay, let me see. Did that get moved to the back? There we go. All right. So if we take this and we say we need these two talking to each other, boom. There has to be some type of translation layer right here, right? So this is what we're doing right now. This is kind of that wrapper that we basically take the Rust Vertex library and we wrap it in a bunch of functions that now map up to ROS2's interface. So people who are using ROS2 just go, oh, ROS2 Vertex plugin, I now have the ability to set up these peer networks, right? So this is kind of the model that we're going after here, is we're going to have lots of these SDKs. ROS2 would be one of those SDKs in gaming. Oops, come on, work with me here. There we go. In gaming, we would have our player mesh SDK, which you're going to have multiple versions of this, right? You're going to have your Unity version. You're going to have your Unreal Engine version. You're going to have your Godot version. You know, we're going to have all these different versions. We'll say Bevy because I like Bevy. We're going to have all these versions of SDKs. And each one kind of has its own flavor. So it's not as simple as just saying, hey, just take our Rust library and use it everywhere. You've got to wrap it into whatever the use case specific framework is. So in robotics, you know, the most popular one is ROS2, or ROS, but ROS2 is the latest version of that. But there's also like Dimensional OS. OpenMind has their own operating system that's kind of an Android style operating system. So everybody's going to have their own operating system. And what we want to do is we want to build multiple SDK wrappers for this. So that being said, and this will kind of help with the update today, an example of one of these wrappers is actually FoxMQ. And this is, if you've been in the Tashi space, you're familiar with FoxMQ. But FoxMQ is effectively an MQTT broker wrapper around the Vertex library. So what this means is if you're in the IoT space, you're familiar with MQTT. This protocol is a message queue transport protocol. And this is what is used in cameras, thermostats, security systems. There's lots of places MQTTs work. Even in some robotics, there's the use of MQTT. So what we did is we basically said, well, hey, listen, MQTT is a very common, well-established, relatively simple interface protocol. Why don't we just wrap Vertex in that protocol, and we'll give it a new name, a new commercial name, and we'll call it FoxMQ. There's a little bit of a joke behind this. One of the more popular MQTT applications is called RabbitMQ. And we were like, well, what's the natural predator of a rabbit? And it's a fox. So we called this FoxMQ. Plus, foxes are cool. Like, everything about foxes are cool. So we have FoxMQ. And that's basically a wrapper around Vertex. Okay, so currently we have this thing called Vertex, and we have this thing called FoxMQ. That's what we've got right now. We've got a couple versions of player meshes, and we've got a RoboMesh that's in the work right now, RoboMesh SDK that's in the works. This is the community update. Is Vertex has been getting rewritten, refactored, and so it's in a much better state for inclusion in other types of frameworks. And so we had a huge update recently that makes it much easier to wrap it and put it into other frameworks. Also, we're updating FoxMQ with Vertex in it, and we're going to open source all of the code of FoxMQ so that anybody who sees the Vertex library can go, how do I write my own SDK? And that's what we're going to want to do is like, we could go out and write all these SDKs, but that's a lot of energy on our part. And we've got multiple layers to this technology to focus on from a technology perspective, from a development perspective. And so that's really not super scalable. It's doable, but it's inefficient. But if what we can do is basically use FoxMQ as our reference implementation of Vertex, meaning that anytime somebody says, hey, I like what you guys are doing with Vertex, I want to build a dimensional OS SDK for Vertex. How do I do that? We would go look at FoxMQ and see what we did to make that work with the MQTT interface. And then you should know how to wrap Vertex in an SDK. All of the examples, sometimes we can put up all the documentation in the world to kind of academically explain what we're building. But until you see it in practice and in code, sometimes it's hard to wrap your head around what we're doing. And so that's really what's been going on the last couple of weeks, is really been focusing on buttoning up Vertex for easy inclusion in other SDKs, and then refactoring FoxMQ to include Vertex in as a reference implementation, so that anybody can look at it and go, I see how Vertex works. I see how you would include it into a project, and I see how I would frame my project or my SDK for other people to adopt. So anyway, that's kind of the what have we been working on the last couple of weeks, and what we're going to be working on here for the next few weeks. I suspect that this is going to be ongoing till mid-February. So expect to see some updates to our docs and see some updates to our GitHub repos in February. So the refactoring is happening through mid-February, and then I'm probably going to be leading a team on documentation updates and GitHub updates through February into maybe early March. So that's what's going on right now. And the reason for this, let's be really, really practical about why this is important. As we're building out the network, the lattice layer, we need demand. We need people using the technology. We even had somebody in Discord today ask, how do I get access to the Lattice Relay API? And the answer to that is you don't yet. At some point, we're going to expose that. But quite frankly, this Vertex SDK the Vertex library in an SDK, so if we have the RoboMesh SDK, the RoboMesh SDK should handle most of the hard setup stuff for connecting with Lattice, right? So you should be able to go put a credit card in at a gateway, get an API key, put it into the SDK, and it just works. You don't have to think about how to set up the relay. So that's the direction we're going, is we want this to be so seamlessly easy for developers in the spaces that they're familiar with. We're not trying to ask them to step out of what they're familiar with. And this, quite frankly, has been one of the major challenges of blockchain in general. In many cases, if I'm building a project and I'm in C or C++ and somebody goes, oh, now you got to write some Solidity code and deploy that as a smart contract, like immediately I'm like, I have to learn a whole new thing. Yeah, no, thank you. And so it's been a major friction point. Those who are Solidity developers, you're good at what you do. You're good at your Solidity. But those of you that are ROS2 developers aren't interested in learning another language and deploying a new entire deployment stack and a new maintenance stack and a new cost structure. Like, that's not part of what you're trying to solve. You're trying to solve for robots. And so that all being said, we're going to where the developers are, And we're building this in a way where they don't have to think about blockchain. They don't have to think about keys. They don't have to think about consensus. All they're thinking about is, I've already got the framework I'm familiar with. I'm adding a plugin, putting a new API key in, and it should just work. And walk me through all of the complicated setup steps. Do it in a way that it becomes seamless and non-complicated. And the ideal scenario would be that the SDK auto negotiates all of the relay connection details. Like, you shouldn't even have to put in IP addresses or domain names for relays. That should be baked into the SDK. There should be a lookup capability and auto provisioning, checking telemetry for performance and stuff like that. So to the person who asked, how do I get access to the relay API? The answer is, that's not really the direction we're going right now. We're going the direction of, when you use one of our SDKs, you don't even have to think about relays. You don't have to think about anything. Like, if you're using the player mesh SDK, you don't think about lobby for setting up a new game. It just provisions for you. And you don't have to think about, what if my players are behind firewalls. It just negotiates that for you. It does the tunneling and the traversal, the network traversal for you. So that's, I mean, what we're trying to do is, we're thinking very commercially this year, right? Last year, we've been focusing a lot on building the community and awareness. We're still in technically season 1 of our missions program, which is focused on awareness. And we talked about season 2 really being the season of growing supply, and season 3 being growing demand. But we can't wait till season 3. We have to build demand today. So while season 3 will add additional focus to the demand calculation, right now we're just like, well, we need to have the tech ready for that. So while we have the pieces ready, Vertex is a thing, Lattice is a thing, FoxMQ is a thing, we have to build it in a way where other people can expand the technology stack for us. So we're not solely responsible for building into robots, gaming, IoT spaces, right? Those are things that other people can do for us, and we're showing them how to do it. And then we can handle all of the Lattice stuff after that. And the cool thing is, suppose we get a few customers using Vertex. When we get the supply up and ready and connected, like, the demand's already there. And we've got customers right now who are saying, we want these libraries, we want these SDKs. And so that's kind of driving the direction we're going. We have a lot of robotics pressure right now of people who want this ROS2 plugin. So that's part of the reason why we're rewriting Vertex, to make it easier to build these SDKs. We have a few customers who want an MQTT interface. And so we're building FoxMQ and refactoring it. And we're actually using it as the reference implementation, so anybody else can build on top of it easily. We do have a number of people in the gaming space who want to use the SDK. I think sometimes with gaming, it's just a matter of timing. A lot of these developers are in the early phases, and so they're not ready to either implement, or maybe they're in the later phases and it's already too late for them to kind of change their net code at this time. So they're going to revisit that later. So gaming is an interesting space. I think we've already got kind of a Unity starter SDK, but we need to go back and refactor it for sure, especially with Lattice in mind. We need to refactor these. And honestly, we're probably going to put out some bounties or hire somebody on contract to do these SDKs. And then we'll have to set up a whole separate biz dev team to go after the gaming space. It's just a longer sales cycle. FoxMQ is very self-service, and Robotics is very self-service. So when we build these libraries, we show people reference implementations and how to build in it. They tend to be able to pick it up and run with it. Gaming's a little more handholdy, and you have to like have some more presence. So we're getting there. It's all part of the grand strategy of things, and gaming is where we proved out the capabilities and the value of this. But just to be clear, we're very commercial right now. We're thinking very commercially right now of what things do we need to build and get ready to create the demand that will satisfy the supply that you guys are building out right now. So, okay, cool. So I do want to talk, though, a little bit about some differences in consensus, because that plays right into why we're building these the way that we're building them. So just to give you, well, going back to maybe the design before here, remember we were talking about in a multi-robot scenario, each robot is going to be running Vertex, right? I want to talk about how this is different than maybe what the rest of the blockchain world is doing, and maybe uh, even what FoxMQ is doing differently. So there's kind of like three layers here that we can talk about. But let me go ahead and I'll kind of zoom out a little bit and we'll talk a little bit about this, because I think this is good for you guys to know in general, and for all of our community to know, because um, you have to be able to understand, to communicate what we're doing to other people. And I think it's useful to understand how things are different. So if we go and we say one of these boxes is a consensus box, right? What's boo, 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 boo. That's too small. Okay, we're just going to do this, right? We're going to say there's a consensus box. It's a flattened diamond. All right. So if we look at how blockchain does this, and this is how most blockchains do this, what you have is you've got now this can be multiple models, right? But generally what you have is you have, we'll call this a server model, right? You have a consensus server, and then you've got clients, and maybe we'll even call this wallet, or DApp. I like DApp, right? And so this is going to be the client, right? So it's a very server client model. This is most scenarios, and this is how you make it practical, right? Theoretically, every wallet could also be a server, right? In most blockchains, you can also be a consensus server. I used to do this back in the early Ethereum days. I wouldn't use a third-party wallet. I just ran the Parity wallet, which ran an entire Ethereum blockchain server, and I would download the entire state of the blockchain before I engaged with it, and I only worked on it locally. And that took sometimes hours to update. If I hadn't logged on for a few weeks or months, it would take a while to get updated, or if I was installing it on a new computer. It's very inconvenient, and I think it worked fine for those of us that were purists, but it kind of sucks for anybody else in the world. The fact that you have kind of like this multi-hour on-ramping process. I know there are ways to streamline this. You can take like the heads of the blocks and use that cryptographically to show that things haven't been mutated. Like there's all kinds of fun stuff you can do. But if you were going to run a full server, you want to know like the full state of the blockchain. And certain blockchains don't even have that option, right? So if you look at like, you can be an indexer on certain blockchains, but if you want to participate in consensus, sometimes you have to qualify for that through staking. I'm thinking of like Hedera, Solana, Algorand, and they do that for performance reasons. But in that scenario, you can think of it like this. You've got these consensus servers, right? And these consensus servers are all synchronizing with each other. And I'm just a little old client here, right? And as a client, I'm going to talk to one of these servers, and they're going to talk back to me, and we're going to reach consensus. I'll go back that way. There we go. And I'm going to submit my messages to this server, and these messages, can I add? Yes. And these messages will reach consensus in the blockchain, kind of a black box to me as a client. Now, as a client, I can talk to any one of these servers, and theoretically, I should be able to get the latest state of whatever's going on, right? So theoretically, I should be able to query. And actually, let's change this. Let's make this transaction. So I submit transactions to a server, and I get updates from that server. But I should be able to query any blockchain server and get the state of whatever my wallet's balance is, whatever my position in that ledger is. Because really, what we're doing in this blockchain model is we're synchronizing a ledger, and a ledger is effectively a database of accounts or addresses and balances. It gets a little more complicated when we get into smart contracts. Smart contracts have their own kind of virtual ledgers or sub ledgers where they can kind of keep track of their own state, which includes like, okay, your address is now engaging with this new smart contract, and this smart contract represents a token, and you now have an integer that is your balance relative to this token. So smart contracts are basically sub ledgers inside this massive consensus ledger, right? But the thing here is that you are submitting transactions. It's taking some time for these nodes to reach consensus. And at some point, you're going to query the state of that ledger and update your wallet or your dApp, right? This is why it takes time. It's pretty quick to submit a transaction. I mean, we're talking milliseconds, sub-milliseconds in some cases, to get a pre-approval from a consensus server, right? So when you submit your transaction, there might be a pre-approval state where the consensus server will, and when I say consensus server, I'm talking about a blockchain node, right? This is the blockchain nodes that you're talking to, or the RPC interfaces. And so when you're talking to that node, you're basically going, hey, I, with this wallet, want to send money to this other address. From my address to that address, I want to send some token balance. And the first thing it's going to do is it's going to pre-check you, right? It's going to do a pre-process. It's going to say, do you even have enough balance for this to work? And it's going to go either no or yes. If it's no, you're going to get an almost instant response, right? It's sub-millisecond times. Add a few milliseconds for network latency, but you're going to get an instant response going, sorry, you don't have enough balance for that. If you do have enough balance, you're gonna send the confirmation with the signatures from your wallet, and it's now gonna go, oh, okay, he does have enough balance, and he has authorized me to go ahead and initiate this transfer. And then it's gonna go through the consensus process with the other nodes in the ledger, which can take seconds, and in some cases it can take minutes. But if we look at, and a lot of why we build L2s is to speed this stuff up, right? Side chains and L2s, we build those to speed this stuff up. But usually when you build an L2 or a side chain, you are adding adding complexity and reducing trust. So anyway, that's a discussion for another day. But in this case, it might take a few seconds for all of these nodes to agree on the update. First of all, we have to check for double spends to make sure you're not submitting a transaction to two nodes at one time. We have to deduplicate them. Sometimes they do get recorded into blocks and get confirmations. And then when there's a convergence, one of those blocks is getting pruned, right? So there's all these processes about, okay, how do we agree on how we're going to change the ledger? That happens in these servers. But we still have this client server model where the client's just sitting here waiting to get an update. It's trying to look at this and go, okay, have you guys got enough confirmations for me to feel comfortable about this? Because, the first confirmation might just be like, okay, at least one additional node has seen your transaction and added a block to it and said, I accept that transaction. But there might be a fork going on. There might be other forks where you have other nodes that are seeing different things, maybe a double spend, that haven't confirmed you yet. And the idea is that after a certain number of confirmations, it's unlikely. The more confirmations there are, the less likely it is for your transaction to get rejected and for your transaction to continue on. So it's a confirmation model. And sometimes I like to draw this, and I like to say, okay, say this one is your transaction block, right? So this is the block that contains your transaction. And then you're going to have a confirmation block, which is the next block. And we'll say confirmation block 1. And so what's happening is you've got multiple of these blockchains getting built. And quite frankly, you might get another block over here. We'll say alt confirmation block over here. And it might start building its own chain. You might have two chains. And then the question is, which one is the longest chain the fastest, right? So if this one gets longest chain, everybody might suddenly accept all of these. So they might go, okay, for all of these, we're going to go ahead and accept those. But these transactions over here, these blocks, these alternate blocks that are kind of competing for confirmation are going to get rejected and pruned, just because this is the longest chain of blocks. But the idea is, this is what you're seeing here, is that somebody is creating a new block that is pointed to a block that is pointed to the block that your transaction lives in. And the longest chain of blocks is the winner. And there will be other chains of blocks. The question is who's going to get the longest chain and who's going to get the majority to adopt that chain. So as soon as you've got like a few extra blocks over here, everybody's jumping on this chain and adding their blocks to this chain because it's the longest chain. If they start adding their blocks here, there's a chance they might lose out on their compute opportunity. So they obviously want to compete for the chain that's going to win them the reward. So that everybody's going to start adding their blocks to the longest chain. So it really is a race to find out who's going to add more blocks. Now, that being said, there's nothing to say that what if out of nowhere we got a bunch of extra blocks here, right? And this became the longest chain. Now suddenly that first block, that first chain is not the longest chain anymore. And this is now the longest chain. And this is the one that gets pruned out. That's a real likelihood. It's a small likelihood. And that's why we talk about after a certain number of confirmations, we can generally trust that this chain is going to be the longest chain, right? After 6 confirmations, usually in Ethereum is what we generally look for. For certain financial transactions, they wait sometimes as many as 20 transactions. Sometimes people are okay with 3 or 4 transactions. Your wallet generally, it depends on the wallet provider, but generally your wallet software will do something like 3 to 6 transaction or confirmations. They'll accept it as a finalized transaction. And then you just keep operating as if it's finalized. But there's a small chance that another chain comes by and undoes whatever your transaction chain was in, right? So there is a scenario where with very, very small likelihood that your transaction does not get finalized because it wasn't included in any of the blocks of the longest chain. Now, that's unlikely. The vast majority of the time, as soon as you get a certain number of confirmations, you're golden, and it's been pretty efficient. But there's a scenario where forking can happen and your block is not finalized. And this is why we call confirmation style blockchains, we call them probabilistic consensus. And to be fair, most blockchains, and I think most even consensus algorithms are probabilistic, but there's always this question of like, what's the probability of it? Is it a probability of 1, which means that it won't change? Any probability less than 1 is a chance that it will change. So with blockchain, you might have a probability of like 0.9999995, right? And that just means that you have this really tiny chance that your transaction gets unwound. But it's so tiny that we just say, it's good enough. We're just going to keep moving. The chances of my transaction not being finalized is so small. I'm just going to keep moving ahead, and everybody's going to treat it as if it's finalized. But that's kind of in certain scenarios, even that small chance of it unwinding is too much of a risk. And I think that's probably why a lot of banks are looking for blockchains that have finality. And when we say finality, in most cases, that means either a deterministic finality or a probability of 1, which means that it is still technically probabilistic, but once you get a probability of 1, that means that it can't be undone. It is final. And so there is no probability. That's basically saying 100% confirmed is what you're saying when you say probability of 1. In most traditional confirmation style blockchains, you don't get a probability of 1. Now you do have things called like PBFT or PBFT derivatives or like Raft or I think Raft actually came before PBFT. But you have a lot of protocols out there that will have a PBFT, which is a practical Byzantine fault tolerance confirmation model. And by practical, it means like it's not a probability of 1, but it's good enough. And so there are different styles or different flavors of that style of consensus. But that one's actually a little bit different when we think about PBFT. It's still a client-server model, but with PBFT, they're effectively voting. And you see a lot of stake-based, proof-of-stake protocols using PBFT style things. But effectively, we're now voting between each other, right? We're going to add some arrows here and stuff. Oh, the arrow's being weird. Stop being weird. There, we'll do that. Right, so these guys are all voting between each other. And there's different ways to do voting. I don't need to get into a lot of that, but there's multi-round voting. There is a proposal and confirmation style voting. So what will happen a lot of times is you're still building a blockchain. You're still building this block. But the question is who gets to write the next block? And there might be a proposal and confirmation model. There might be, what's it called? Verifiable random functions, VRF. right? VRF for how do we select the next block producer? Who's going to produce the next block? You can use different methods for choosing that. And that's effectively what we're doing is in blockchain, we're trying to decide who selects the next, who generates this next block. In proof of work, it's a math problem that everybody is racing to solve to create the next block. And a lot of other protocols, even including things like PBFT, there might be a proof of stake mechanism and some type of selection algorithm. And sometimes it's a random selection algorithm. But the goal is to prevent people from predicting who the next block producer is going to be. So you might have like a PBFT model where, we're selecting, somebody gets selected to create the next block. They submit a proposal of the next block. They capture some approvals, some subset of other nodes who get to approve it. And if you get enough approvals, it gets confirmed, right? And so there are different models of PBFT. If you think about voting, this is always a tricky one. If you think about voting, you might have like we'll say that we've got a proposer, and then you might have voters, and then you're going to have the tally person, right? And so if you've got multiple of these voters in here, what's really happening is the proposer might be coming in here and saying, hey, I'm proposing this block. Everybody, I just want you to know I'm proposing this thing. The voters are all going to cast their votes, and they're going to pass their votes. Oops, let's try this again. They're going to pass their votes on to the tally, whoever this is, and then the tally person is going to do is going to basically take those votes and compose a proof of some sort and send it back out to the world and say, hey, we've got this proposal that has been voted on and confirmed. But you'll notice a couple things here, like the proposer is a leader. The person doing the tallying is a leader. So we're trying to select the next block producer. We're taking a bunch of votes, and then we're selecting a tally participant to tally up these votes. And this is kind of what Raft is. Maybe this is an oversimplification of how Raft works. But the idea with Raft is you're choosing a leader whose job it is to collect votes on proposals and make that the final next block, right? So that's effectively what we're coming up with, is we are generating the next block. And it happens through this kind of proposal voting tally process. Notice, first of all, how many steps there are here. And second of all, notice that we've got leaders here, right? And sometimes these are the same. Sometimes the voters are also the proposer. Sometimes the tallier is also a proposer. But the idea is somebody's selected, and we got to randomly choose who's going to generate the block, the proposal. And then you've got a bunch of participants who are going to vote on, is that a valid block? And then you've got the tally participant, who's effectively the leader, who is going to count up the votes and compose a proof and then submit that to everybody back as a block, and everybody will accept it because it's got all of their signatures on it, right? So that's another way. This is kind of a PBFT Raft style proposal confirmation model. But you've got multiple communication steps. Okay. And as a client, as a dApp, or as a wallet, in all of these, I'm still talking to one of these servers. And I think that's probably the most important part here, is like, I am still an outside participant, right? If we want to have any type of scale, unless I want to host an indexer or a consensus node, which can be expensive and it can be costly or it can be full of friction. Like you have to go through an approval process potentially. Sometimes it's through DAOs. But to become one of those node operators is not always super simple. That's why a lot of people like proof of work, is because anybody can host a server in proof of work. You might not get rewards, but at least you can independently validate the consensus all the way back to the beginning. In a lot of these other models, you are a client because you can't host a node. You might be able to host an indexer, which allows you to index all of it, which is similar to what you would do in a proof of work, except for you're not participating in consensus. You're an outside observer. So you can kind of go, if we come in here and we say, put a dotted line on that, and we'll just say indexer, and your wallet could query, so it would still submit transactions over there, but say we come in here and we say query here and transactions here, right? And this indexer is receiving updates from the consensus nodes and stuff. But we're adding lots of hops here, right? There's lots of participants. There's lots of message hops here. If I submit a transaction, it has to go into a mempool that then gets picked up by a proposer. Proposer has to include it in a block proposal. It has to get voted on. Then it has to get tallied up, and then it gets finalized as a block. And then that gets dropped into an indexer, and now I can query that update. The cool thing about this model is you don't need to delay. People can vote as fast as they want. The tally server can tally up as fast as it wants. So these can generally be much faster. It's just a matter of timing of like how long does it take to collect votes. So this is why you see the difference, right? If you look at proof of work tends to be pretty slow, like on the order of tens of seconds to minutes on proof of work blockchains, because it has to be slow to prevent too many forks in the longest chain scenario. You don't want to prune forks as much as that. And then you have voting algorithms, which is what we'll talk about. This is kind of like the Hedera model. And then you have kind of like the Raft PBFT style proposal and confirmation model, which can be really, really fast. And this is why you see some blockchains saying, we can get 500 milliseconds of latency. And this is what they're doing. Now, in this scenario, you can get finality, right? If you've got somebody who is the tally person, they are calculating the votes, and you can get probability of one finality, right? And now you can trust what is in this block, and that's fine. The risk here is what happens when the leader is compromised or when the leader is a bad actor. The answer that Raft has is it just chooses a new leader, right? So you just, find another consensus node and you make it your leader. And that's fine too, right? But you still have a leader. And this is where like the Hedera hashgraph model is very different. In the Hedera hashgraph model, you as a client are submitting your transaction to one of these servers, one of these consensus servers. The algorithm itself handles all of these steps here. It's actually a virtual voting algorithm. And without going into virtual voting too much, effectively what's happening is these nodes are spamming each other as fast as possible with any new transactions they get. They're independently running this algorithm and independently calculating the order of all of those transactions, which effectively is consensus. So they're getting the same order of transactions with the same timestamps, with the same signatures, proving that everybody has seen these transactions, or that a sufficient number of nodes, in this case we'll say 2/3 of the network has seen these transactions before we consider them finalized. And finalized meaning actual finalized, right? So probability of one finalized. So it's incredibly efficient on the calculation side. You don't need to have multiple stages of proposals, tallies, and confirmations. It's just everybody spams each other as fast as possible, and everybody independently calculates the order of messages. And then I, as a wallet or a dApp, am talking to that network. Now, Hedera has multiple layers, right? They've got their mirror nodes, which are effectively indexers. So you can actually... The consensus nodes manage the consensus, and then you have mirror nodes which handle the state of the network, the persistent state of the network. And then you talk to that mirror node or indexer to do queries. So you do you do all your transactions to the consensus nodes, and then you do your queries to the mirror nodes. And Hedera is incredibly fast. I think they're down to like 2 to 3 seconds per transaction for a full global network. This is all great. Now here's the problem, right? You guys ready for this? Client server model means that the client is renting compute cycles from the network to maintain and calculate updates to a ledger. This is not free. This right here comes with a cost, and we tend to call that gas, right? We're familiar with it. If you've been in the space, you're okay with it. What we're looking for low latency and low gas cost, right? That's what we're generally looking for. And that's not always the case. Sometimes the value of the network pushes us towards proof of work networks, and that's okay. Sometimes there's enough value on the network that we're like, listen, everything I want to do is over on Ethereum. all of the liquidities on Ethereum, I'm okay paying a little bit more in gas fees for Ethereum. L2s obviously add some performance. L2s break a whole bunch of stuff though. So we're not going to talk about L2s, but L2 is like an additional bolted on solution that violates a lot of the trust promises of the core L1. Unless you can figure out how to use or leverage the same trust model in your L2, which by the way is what a lot of L2s on Hedera are doing. They're leveraging Hedera's consensus service, HCS, to build their L2. So they're actually getting a lot of the L1 trust in their L2s. So, but generally what we're looking for is we're looking for low latency, so fast transactions, and low cost, low gas, right? Here's the problem. If I'm a gamer playing a game, I've already paid for the game. I'm not interested in paying for gas. Someone's got to pay for that gas. And in robotics, I might have thousands of robots performing a task and they have to synchronize multiple times in a second. I'm not going to pay every transaction to record that on a ledger, on a public ledger. Now, option one is, okay, I'm going to host a private version of this. I'm going to put this on-prem, and I'm just going to run the entire blockchain stack or the consensus stack on my private servers, and all of my clients can just talk to that. Now, I'm paying for this, which is fine. Now I'm paying for all of the costs of this. But what happens when I have to cross trust boundaries? What happens when I'm trying to coordinate with robots that I don't own? Say somebody else, we're doing fire protection, right? So we're cutting fire lines in high, dry grass in California to prevent fire from spreading into living spaces. And I need to provision a bunch of robot lawnmowers, right? These autonomous lawnmowers that belong to homeowners to come out and cut the fire line. Who's hosting this? Who's managing the coordination? Is that all done by California CAL FIRE? Is CAL FIRE just hosting servers and they just provision this? Do they even need a blockchain at that point if CAL FIRE is managing it all? Probably not. But how do I, as a robo lawnmower, know or can validate that I'm getting compensated for the work that my robot's doing, that my robot's not being provisioned for fraudulent or illegal actions? How do we capture identity stuff? Like, there's all kinds of questions that really are a good fit for blockchain. How do we do settlement and signaling? There are a lot of reasons to have a blockchain for this. And the Tashi answer is very different. And this is where I want to draw the huge distinction here, right? So we've talked about different styles of consensus and confirmation and the relationship. First of all, choosing leaders in your consensus, but also the relationship between clients and servers. What happens if we just take our clients? By the way, this is the answer that Tashi has here. We're even going to call this a dApp, right? But we're not going to call it a client anymore. We're going to call it a peer. What happens if we just take these peers and all of the peers are running consensus? There it is. Boom. We're just going to put a little consensus symbol in the corner here to say that this peer is not just a client. It is also running its own consensus. As a matter of fact, we're going to put it in the middle because we're going to have these guys communicate with each other through their consensus. What happens if your robots are running consensus on their devices in their operating system via an SDK, and they can just communicate directly with each other and never talk to a blockchain and never talk to a server? It's the clients who are synchronizing between each other, or the peers, as we like to say it. We got to add them here too, because they're talking to each other in between. So this is the scenario that Tashi's talking about. Because what happens here? If the reason why you're paying for gas is because you're renting somebody else's compute to calculate consensus, what happens when you're using your own resources to solve a problem that your own node is participating in? Well, gas goes away. That's step one. So if I'm running consensus on my robot, or I'm running consensus on my gaming computer, or on my own home hub that is managing my IoT, and another robot is running consensus on their device, as long as the application that sits on top of this consensus is compatible, meaning that they have a way to coordinate efforts. So there's going to have to be an SDK. So remember, we were talking about SDKs earlier. There has to be an SDK layer that sits between the application and the consensus, or in other words, wraps the consensus, that now allows this consensus to synchronize the state of these robots between each other. So a good example would be, our whole scan, plan, and execute model for robots. If this robot is scanning a particular area on the map, like all these robots show up to the same GPS location, right? And this one scans a particular vector of the land, knowing what the map layout or the terrain layout might be, and this one scans another. Could they overlay those scans and create a real-time map of the terrain that they all have to attack? Yes. So we can now have multiple robots scanning an environment who are owned by different parties, who we're crossing the trust boundaries now because they're owned by different parties. They can now scan and share what they've scanned, and now they can agree on the plan, meaning, okay, knowing what we know about this space, we just scanned using LiDAR and visual cameras and infrared. We now kind of understand the terrain and all of the flora and fauna that is on that terrain. We now understand what we're dealing with. We've scanned and shared that. Now we're going to share the plan. Let's make a plan. You're going to go over here and look for this. I'm going to go over here and look for this, and we're going to make this path around that rock to the other side, and we're going to rescan on the other side of the rock because maybe that rock is a ridge on a mountain or something and not just a big rock. So they can now start to scan, share their plan, and share their execution. They can say, here's the update on my execution, and then rescan, replan, and re-execute. And so they get to continue in that cycle over and over again. So that scan, plan, and execute works really great for robotics. It's the same thing for gaming. It's the same thing for IoT. It's the same thing for AI. We have to share some amount of state to enable us to generate a plan for us to execute some problem-solving solution. And I think this becomes really, really important because, think about this. We just got rid of gas because the robots, the peers themselves, are calculating consensus. So gas is gone. So now when I've got 1,000 robots spamming each other with 1,000 messages a second each, so we've got, 10 million, whatever the number is, millions of transactions a second being spammed to each other and having to be ordered and synchronized, that's doable with a local consensus. You don't have to reach out to anybody else and wait 2 to 3 seconds or even 500 milliseconds for that to happen. And you're not paying for every one of those transactions because your expense is the cost of the compute. Your robot is performing compute, so you don't need to borrow compute from other nodes to do that. This is the Tashi difference right here, right? And here's the cool thing. There's a few cool things. A, lower costs. B, higher throughput, because we don't have multiple layers to go through. We don't have multiple bouncing arounds to do. We don't have indexers that we have to update and talk to. The peers are synchronizing and updating directly. So we have a performance gain. We have a cost efficiency gain, meaning that the gas doesn't exist. It's just the cost of the electricity for the compute on their devices. And additionally, we've got a scaling potential gain here where you can grow these networks to different sizes to solve different problems. So you might have parallel problems being solved that don't all need to go through a single blockchain. You now have multiple sessions or groups solving different problems that all add up to a much larger problem, right? We can break the bigger problems into smaller problems and have smaller devices participating in the solving of those. And here's the cool thing. Depending on the size of that, we'll call it a quorum or that session, you also get every other peer validating every other peer in that session. In other words, these 3 peers are validating this one peer's work. So when he scans, plans, and executes and says he's going to do something or he does something, you've got 3 other participants who are watching that and going, okay, we're going to validate that. We're going to add our signature to that and say that that this is happening. Now, we're going a little bit over the hour. But I want to continue with this for a little bit longer because I really want to make the point of why the Tashi difference is so important. So, all right. So we've got. I'm just going to put this up here. We've got no gas. We'll say increased, or we'll just say scaling. We've got reduced latency, and we've got inherent validation, meaning that they're all watching each other anyway. Like this is what we get from this model here. And so I think this is these are key differentiators. And here's the cool thing. We've got inherent validation, which could result in a state proof, meaning that all of these peers are signing some state, some proof of the state of the entire problem space that we're trying to solve. And we can take that state proof and hand that to an L1 or L2 for signaling or settlement, right? So we can do all of the really hard work strictly peer-to-peer in consensus between each other using this virtual voting algorithm, which, by the way, I have to always give recognition where recognition is due. This is based off the Hashgraph algorithm. There are some other things we've looked at and improved on the virtual voting for our specific use cases, right? So we've really tuned it for low latency and for the type of use cases we're looking at. But this is a virtual voting algorithm, which means the peers are calculating consensus between each other with voting, not with a confirmation model, not with a central tally model, but with a virtual voting model, which is the gold standard of consensus. And we're doing it at a scale and performance that blows away any other L1 or L2, especially when it comes to real world use cases, right? So again, if we can do this between robots, we can do this between players in a game, we can do this between IoT devices. We now have a much more scalable, more performant, more affordable, and I would argue, and this is a big point. I remember doing some analysis of storage on blockchain versus like storage in S3, and in one of our calculations, it was as much as like a 10,000x difference, meaning that it would cost you for every dollar you spent on S3, you'd spend $10,000 in the blockchain we were analyzing, and we thought, well, it better be a really important document, and it better be very important for people to be able to validate that on a public network. There are ways to overcome that, right? But generally, what we don't see is an improvement in cost relative to centralized solutions. Now, there are some good arguments about how you could reduce that cost relative to some of these hyperscalers, because hyperscalers have to also account for uptime when nobody's using them too. So they're paying for electricity even if nobody's using their stuff. So there's always a markup on their costs. So I won't say that hyperscalers are the most efficient, but there are economies of scale that come with hyperscalers. And blockchains generally are significantly more expensive. If you were to store the pure file like a hyperscaler does with 100% replication, like a hyperscaler would do, and by 100% they might do like a 3x replication. But when you have those replication factors and the reliability and that uptime that a hyperscaler will give you, in many cases, the blockchain solution is going to be significantly more expensive. In this case, it actually can be less expensive because the peers are participating in the storage of the state. And so while there could be a third-party cloud provider that is hosting this file, there's going to be replication in the cloud anyway. Why not have that replication on your peers? Why not have your files either striped and shared across the different peers, or actually, no, I'm going over here. I need to hop off of this because I actually have a call that's starting right now. But the point being is that there are some incredible efficiencies that come with this, right? Not only is there no gas, but you're also going to get storage efficiencies relative to Web 2 solutions. So the reason I bring that up is like in the gaming space, we actually saw that building multiplayer gaming like this actually saves game developers a bunch of money. And I suspect that would be the same thing in like self-driving cars for intersection traffic negotiation type of scenarios where you could host servers that manage all of the traffic negotiation, or you can allow the peers to all do it and validate each other, and the storage efficiencies kick in. So anyway, I wanted to really just highlight the value proposition here. And right now, FoxMQ, effectively, these are all MQTT brokers, right? And you could have let me get this done here. There you go. You can have everybody owning their own broker, right? I could have one, you can have one, so and so can have one. We all have our own brokers. And then all of my IoT devices are just talking to my own brokers, right? So if I've got this IoT device, multiple IoT devices, they can all be talking to my broker. And we now have a shared MQTT stream, meaning that anything, if I've got cameras, if I've got sensors, yeah, let's talk sensors. If we're tracking weather patterns or flight traffic, I'm hosting my own broker. I've got my own sensors on-prem. Maybe I've got weather, maybe I've got air traffic, maybe I've got humidity or pollution, air quality. So weather, air quality, and air traffic, all talking to my broker. And you've got the same or similar devices. We now have a shared view of whatever our sensors are detecting. And through our MQTT brokers, we can now share that information, coordinate it, do it in a private way. So this is FoxMQ is basically a way to give you your own MQTT broker and to integrate with other people who have their own MQTT brokers. So I just wanted to demonstrate how Tashi is different than all the other consensus protocols and consensus models, and how FoxMQ is kind of like an implementation of the core technology to really give you a reference to figure out how this all works together. So, okay, I am actually running way longer. I got to hop on another call. I apologize for that. But real quickly, I want to go through and answer some questions. It says here, are you happy with the updates the last weeks, and is everything running as expected? Nulch is asking that. Yeah, I mean, I think coming into 2026, we had kind of a realignment internally to make sure that we are putting ourselves in a position commercially that will create a sustainable business model for the entire Tashi network. One of the core discussions we had was the idea that in season 3, we're going to focus on generating demand. But we need to have that technology now, and we need to start bringing reference customers on now. And so we looked at our entire stack and said, which customers are ready to implement the soonest, and what tech do we need to prepare now for that? So there was a little bit of a realignment. We've been really focusing on Lattice and building the community and getting the nodes out. But over the last couple of weeks, our real focus has been on how do we prepare our technology for the demand side, so that when we are ready to flip that switch in season 3 and really go out and market to that community, the technology is ready to go and the infrastructure is ready to go. So expectations have changed, Nulch, if that helps, but they've changed in a very logical, reasonable way. Nulch says, these ways of going through different topics every week is an awesome way of learning about Tashi details in deep. Thank you, Ken. You are welcome, Nulch. I love doing these. These are always fun to do because I love to get into the tech. And, I'm obviously bullish on Tashi, but I honestly think that there's nobody else solving this problem yet. And this is the missing piece for all of Web3. And if we want to clip that and highlight that comment I just made, I'm happy for that. I'm struggling to see where public ledgers, L1s and L2s, are going to be useful in mainstream industry until we solve this edge problem. And I think Tashi is solving that edge problem and creating the connective layer, that substrate that will make Web3 useful to the rest of the world, which means all of us who are participating in Web3 for aligned incentives and distributed incentive and economics get to participate in that. So, Crypto Hunter, thank you for this episode. It's an absolute pleasure for my knowledge craving brain. Anytime you guys want to go deep on stuff, I'm happy to. I felt this was important because it's hard to sometimes see the updates when we're working on things like refactoring code and documentation. Sometimes people feel like things aren't progressing. We are so freaking heads down and cranking on this stuff, but it doesn't always feel like that. And so I felt like this week was the perfect time to say, hey guys, we are working on a refactor. We are working on getting Vertex ready for demand side. We are working on SDKs and preparing it for scalability of SDKs. But let's talk about why that's important, right? So I wanted to really dig into the why it's important that we're doing this, and really differentiating it. So it doesn't feel like, oh, we're just building another blockchain. It's like, no, we're actually building industry solutions. So, all right, everybody, well, thank you for your time. Sorry again for going over. I got to go hop on another call. So thank you for joining, and we will catch you not next week, but the following week. So again, next week I am out of town, but the following week we'll be jumping back in. So, all right, everyone, thank you. Cheers. Have a wonderful 2 weeks.